All right. Hello. Welcome back. Are you thirsty? I guess so.
I need it for a lap.
So we're doing a lap today then?
We're doing a lap today. We'll use this later. And you'll get to do it in class too. So, 6.2.
7.2.
Vapor pressure and phase diagrams. Let's go ahead and get rolling here. Maybe. Okay. Wow. What the heck? What's going on here?
I don't know, but it seems as if we broke something big.
Yeah, we've got definitely over here, we've got clearly a good choo-choo train. And we've got a
not good.
Not good or bad, right? Bad choo-choo train. So what the heck happened here? And this is real.
Yeah.
Yeah, this is real.
We have a video of it.
Yeah, we
Proof.
do. And we can actually let's just show it.
Mm-hmm.
Oh!
760. Gewonnen hat Herr Dr. Hilf.
Okay, so what the heck is going on here, Miss Morris? We got something to deal. I sense. Oh, we don't want to play that again. I sense this has to do with pressure. Am I wrong?
I mean, you're probably right, seeing as how we just talked about vapor pressure.
Yes, yes. So we wouldn't be just showing you awesome videos for no reason. I never do that in class. Do you do it? YouTube
Fridays.
Harlem Shake or anything like that. Anyway, we've got a choo-choo train here that is filled with this gas, and somebody made a mistake and they left the top open. Okay. And when they left the top open, these gases, on a hot day, or they started to evaporate.
Yeah.
Maybe it's like a liquid and evaporates. And these gases escaped. And as these gases are escaping, what's happening to my pressure in here?
So your pressure is actually going down because your gas
Yes.
molecules aren't in there to push up against the walls.
The pressure's going down, and so then on like a cold day, once the, the gas molecules escape, and that leaves less gas molecules in there. We all know more gas molecules means
Higher pressure.
less gas molecules mean
Lower pressure.
So then what happened? We got a cold day here, looks like it, and those gas molecules that were in there cooled back down.
Because it's cold, so what's their kinetic energy looking like?
Less.
Much less.
They're not moving as much, so they're not exerting as much pressure. So what happened is on the inside of this tank, there were less gas molecules than there were on the outside of the tank, which means the gas molecules in the outside tank are going to win out, and they're going to...
Yep. Because remember, we're always under pressure.
Yeah, crush. Yeah, we're always there's one atmosphere floating around us, and there's pressure bearing down us. There's pressure bearing down on that tank. Just air pressure.
Yeah.
Just air pressure.
And normally
caused
there's
that.
stuff pushing back out.
Yeah, and normally it's all balanced, but in this case it was not balanced. So we're going to look at that today, and actually we're going to give you our little video clip right now.
Yeah. All right.
Okay.
All right. Good.
Okay, guys. So the purpose of this lab is to demonstrate the power of air pressure. What I've got is I've got a soda can filled up with a little bit of water, and I've got a blowtorch. I'm going to heat up the water, and as I'm heating up that water, all the gas molecules in here are getting, all the water molecules are getting super excited to the point that they can escape the confines of the liquid state, and they can become a gas state. Okay, and as they become a gas state, we're just going to take a little bit of time. And now those water gas molecules are kicking out the air molecules. So all the air molecules are being shoved out and replaced by the water molecules, which are coming from. There it is.
Sounds
now
like...
we got it. You can hear it boiling. So water molecules are kicking out the air molecules. And then I'm going to dump it into this ice water bath. And what's the gas water going to do?
Liquid.
It's going to turn into a liquid, right? And once it turns into liquid, it's going to leave all that empty space of where that air used to be. So you can hear it. A little closer. We are indeed boiling now, and air molecules are escaping, and we've got just water vapor. So here we go. I'm going to take it. I got my glove hand here with a hole in it. That's nice. All right. Here we go. Oh, all right. And so, you can see, not a thorough crush, but it did get crushed, okay? And that's just due to the air pressure pushing in on the can, and there was no air pressure left over to push back out because all the water vapor gas molecules that were in there quickly got cold and they turned back into a liquid, leaving a vacuum.
That was pretty awesome.
Not as big as the choo-choo train, but you should get the point. So let's go ahead and talk about boiling and vapor pressure. Okay, well, we all know pressure, our gas molecules outside. And the thing is, as we go higher in the altitude, what happens to the air up there? As
It gets much thinner.
Much thinner, and another way to say that is just there's less air
Pressure.
molecules, less pressure. So the higher the altitude we actually go up, the lower the pressure. And if you like ever live somewhere or like up in the mountains, it is more difficult to breathe. You guys probably heard this. Think of the Denver Broncos. They play at Mile High Stadium, meaning a mile in the sky.
5,000 feet above sea level.
5,000 feet, and it's harder to play there for guys. And you'll see like the away team, they'll come off the field and you see that they got the oxygen masks, and so there's less air, so there's less pressure up there. The higher the altitude, well, this is going to be a little bit tricky, but let's talk about this first.
Yes.
Okay.
So we haven't actually talked about boiling point yet. But what we do want to talk about is boiling point is, which phase are we talking about?
We're talking about solid going to a liquid.
Liquid going
Liquid, we are talking about liquid going to a gas. Okay, so if I draw, just imagine a little beaker of water here, okay? And you've got this beaker of water, and this is my liquid, and this is my gas, okay? And during boiling, we all know that liquid is escaping.
into a gas form.
Into a gas form. And actually, gas molecules are going back into liquid. At the same time, we can have boiling point is if the pressure outside if the pressure outside is equal to the vapor pressure right here. Stop that. Where are those things going? So we've got vapor pressure, which means basically the pressure of the vapors right in here. And then we've got the pressure outside, and when they are equal,
you can boil.
You can boil stuff, okay? So just for right now, the pressure in the molecules outside and the vapor pressure right above the liquid, they have to be equal for the boiling. So if I go higher in the altitude, that means I'm getting lower pressure. So the pressure outside is going down.
So do I need to have as much put into it to make my vapor pressure equal that?
No, I can actually have a lower vapor pressure, and if I have a lower vapor pressure, that means my water is going to boil easier.
Yeah.
So water, if you're at like a really high altitude, like let's say you climb a mountain, normally water boils at 100 degrees
Celsius.
100 degrees Celsius, or which is equal to 212 degrees Fahrenheit. But if I go higher, the vapor pressure is not as hard. So think of those gas molecules trying to escape the liquid. They're really trying to escape, and these gas molecules on the outside are saying, no, get back in there. Get back in there. But now, the outside guys, they don't have as many guys to push back. So it's easier for these guys to boil out. So it's actually, sometimes if you go really high, like let's say like 2 miles or 1.5 miles in the sky, say
It's down
Denver.
to 87.
Yeah, it can get, so like 87 degrees Celsius, or I'm guessing that's like 180, maybe?
Yeah.
Something like that, 180 degrees Fahrenheit.
There's an equation for it.
There is an equation for it. So the higher the altitude, the easier it is to boil stuff, so the lower the boiling point. And boiling point is just the temperature at which something boils.
Now keep in mind that the boiling point also has its opposite.
Whoa! When the vapor pressure equals the...
Atmospheric pressure.
Let me see, I'm trying to find my mouse. The atmosphere equals...
The atmospheric pressure. So when you have the gas pressure, gas molecule pressure equaling the outside pressure, that's when the substance is going to boil.
If I can recap and talk about my little boiling here, let's imagine that we've got little gas molecules right here. Okay? And they're fighting. They're my vapor pressure. And they can only escape if they beat out the gas molecules out here, which is my atmospheric pressure, PATM.
Mm-hmm.
Okay. Well, the higher the altitude, the higher I go, the lower
that atmospheric pressure, so the less that the vapor pressure gas molecules have to fight against.
Exactly. So like let's say they have 10 atmospheric pressures, I go higher, now I only have 9 and there are 8 or so and so. The higher I go, I lose outside pressure, and then eventually I don't need as many guys here to make out to beat up these guys, right? So eventually these guys can just escape. So the higher the altitude, the boiling point becomes lower.
Exactly.
Kinetic molecular theory of solids. Well, melting point.
Right. So melting point is when we're going to go ahead and go from a solid into a liquid.
Mm-hmm.
So remember, we're moving from those really rigid structures into something that has more energy and moves more freely.
Mm-hmm. So this is kind of cool. It looks like a metal. I don't know what that is. It's a metal that's going straight into, so it's melting right there at room temperature just from the heat of the hand.
Wow.
Which is pretty sweet. And then we've all seen this one. This is ice melting into liquid water. And guess what? Can you know the temperature of that water?
I mean, I know the temperature.
I know the temperature of that water. It's actually 0 degrees Celsius or 32 degrees Fahrenheit. And if you are an astute citizen of the world, we all know this is the freezing point of water.
Mm-hmm.
So the reason why is because if you ever have solid and liquid present at the same time, if you ever see ice floating in liquid, if solid and liquid are both at the same temperature, you can, are both there, they're at the melting point. They're at the
Because if it's any degree higher, you won't have any solid. If it's any degree lower, you won't have any liquid.
There we go.
So the melting point is also the freezing point.
Exactly. Okay, so we can talk a little bit about what solids look like. And solids are kind of cool because they can be in whole different types of structures called allotropes. What is an allotrope? Well, basically it's a different solid form of the same element. So take sulfur. Okay, sulfur is, you remember sulfur is one of those weird ones for its Lewis dot diagram. It can actually make a whole bunch of bonds. So this is S8. And you can see sometimes it can be arranged like this. This is actually phosphorus. And sometimes it can be arranged like this. And depending on its arrangement, it actually changes colors.
So let's talk about a more common form of this.
And this is what you guys have heard, and you could probably tell me what each one of those are. What's this first one?
So that first one is actually diamond, a girl's best friend.
Yes, diamond.
So diamond gets its properties from the fact that they're all in what's called tetrahedral structures.
And this is really cool. This is called a buckyball.
Or the official name is Buckminster fullerene.
I'm not going to write that. But this is really cool because these are tiny atoms. So these are carbon, and each little carbon atom, there's 60 of them. And they form kind of this ball, and they're using them in nanotechnology to make really, really strong, really tiny stuff. Like the idea of making a space elevator. If you were in robotics, that idea what that cord is going to be made out of is carbon nanotubes, which is kind of based on what a buckyball is. So remind you, these are all just carbon. These are all carbon atoms. Nothing different except their arrangement. So we've got a diamond. We can make a really cool nanotechnology strong thing. And then this one, you actually have you have a lot of these. What are these?
So that is graphite.
That's graphite. Where do we find graphite, Miss Morris?
Surprisingly, you find it in pencil lead. There's no lead in pencil lead.
Yes, no. This is very different. If you can tell, these are kind of in sheets. Think of one layer on top of another layer. And these can be, these bonds, the bonds that go up and down, vertical, can be broken really easily. And when they're broken, a whole sheet will go sliding off. And guess what? Every time you write, you are losing a sheet of carbon atoms, a sheet of graphite. So wait, I'm so confused. You mean that we have a graphite pencil and it's made out of carbon and it's made out of the same stuff a diamond is made out of?
Absolutely, and we'll talk about how that happens in another episode.
In another episode, okay. And that's it. We're going to talk more a little bit about phase diagrams and what those are. We are going to share with you how you can make pencil
into diamond.
Into diamond.
We'll all be millionaires.
Stay tuned. Okay, so what we've got here is now a phase diagram. A phase diagram.
So, phase diagrams are just charts that show the temperatures and the pressures for given substances. So we'll have pressure on our y-axis and temperature on our x-axis.
Okay.
Before we get there.
All right. Quick turn sublimation. You've heard us say it before. This is when stuff goes from a solid to a gas.
But no stopping between, no liquid.
No liquid. So we've got S to G. And we all know normally stuff melts by going solid, liquid, and to gas. So this is called sublimation.
And then the opposite of it, so when you go from a gas to a solid, it's called deposition.
Deposition. And you'll see this. And we all know solid to liquid, that's melting.
Mm-hmm.
Liquid to gas is
evaporating
or boiling. And so on and so on. And we can talk about what it means to go backwards, and we'll do that here in a second.
Mm-hmm.
Okay. Please pause this and draw this picture now.
Cool.
Okay. So you've got the picture drawn, and hopefully you've labeled almost everything on the graph. Now this is a phase diagram of CO2. And CO2 is pretty cool because we've actually seen it in most of these states. So dry ice, that's a solid.
Yep. Dry because when it melts, or not melts, when it vaporizes, there's no liquid left.
And it becomes a gas. So a couple things I want to talk about. Everything that's solid, whenever we're going from a solid to a liquid state, we just talked about that. So now draw this on your diagram. When we go from solid to liquid, we are melting.
Mm-hmm. And then the opposite is true. If we go from a liquid to a solid, we're going to go ahead and freeze.
Yeah, we're freezing, right? So you take liquid water and we freeze it. And you can do that. You see how I'm moving left to right now? Well, look at my x-axis. All I'm doing is I'm heating the temperature. So as I increase the temperature, so here I am, say at negative 78 degrees Celsius. And I'm right here. Okay, oops. I'm right there. And as I heat up,
your particles are moving faster.
and it's going to turn into a liquid.
Mm-hmm.
Okay. And then if I start at, say, a temperature of, I don't know, 20 degrees Celsius or something along those lines, and I cool the temperature, I can become a solid. Now, this is actually all happening at an extremely high pressure. Because remember, what the Earth's always at, this is Earth's atmosphere, is at 1 atmosphere. Okay, so this is we're in 1 atmosphere right now.
Yep.
So we're typically operating right along this line. And if you notice,
you don't ever actually cross the liquid at that point.
I never get into the liquid area. So here's my liquid area. This is my liquid. And during 1 atmosphere on Earth's surface, dry ice, or CO2, either exists as a solid, dry ice, or CO2, a greenhouse gas, which, you know, all that stuff, is up in the air. Okay, and we change that by increasing temperature. Okay, let's talk about what it means to go from a liquid to a gas. You kind of already talked about this. This is vaporization.
And then the opposite is true.
The opposite is true. Is when we go from a gas to a liquid, it is condensation. Now, guys, this diagram at first might look a little daunting. You will be experts on this. You will be experts. We'll work with these a lot. It's in your work packet as well. And then let's look at the transition between a solid and a gas. We've done this. Solid and a gas is sublimation.
Right? So remember, dry ice was the example we gave for sublimation. And then to go from a gas to a solid is deposition.
Yeah, it's deposition.
If you need to write down those terms again, that's the slide right before this.
Okay. Okay. So we can move along these things, and let's say, for example, Ms. Morris, I'm at negative 78 degrees Celsius.
That is very, very cold.
It is very cold. So I'm right here, chilling out, and I'll just draw a little X. There we go. And I've got a pressure of about, I don't know, 0.4 atm, so less pressure.
Okay.
And what happens if I start to increase the pressure in the room?
So as you increase that pressure, you're going to slowly move towards a solid.
I'm going to start moving up, I start increasing the pressure, and eventually I'm going to hit 1 atmosphere, and I'm going to become a solid. And when I go from gas to a solid, what is that?
Deposition.
Gas to a solid, I am doing deposition. Okay. Now let's say I'm at, what's going on with this point? This is called the triple point. What is the triple point?
So the triple point is the point at which all 3 phases can coexist.
Yeah, so this is where we've got a solid, liquid, and a gas all existing at the same time. Normally, I mean, you guys are actually pretty comfortable with this. You've seen the boiling pot of water. Where are we? You've seen the boiling point of water, right? Okay, there it is. You've seen the boiling point or a boiling pot of water. So you've got water, and you're comfortable with thinking of how, oh, liquid goes to gas and gas goes to liquid. And you've seen ice start to melt. This is my ice melting. And that is when we're going from solid to a liquid. And maybe you've been lucky enough to see CO2 solid become a gas. But very rarely have you seen where all of these are going on at once, solid, liquid, and gas. But that's where we have the triple point. Okay, this is another phase diagram. This is of water, H2O. And if you notice anything different, let's focus on this line right over here. This one right here, okay? Look at the slope. It's like going downhill, negative slope, versus the solid liquid one, which is going
uphill.
Uphill, positive slope. So most everything in the world is like this. Most chemicals behave like this. But water is actually very different, which gives it so many of its unique and special properties, which makes us better.
So let's take a look at one atmosphere, right? So how we exist normally.
Okay.
So if we draw a nice big red line across it, I've got my solid phase, I've got my ice, I've got my liquid phase, I've got my water, and most importantly, I've got my gas phase, so I've got my water vapor. The cool thing about water, and the fact that water is the exception, is that you can have all three states in normal everyday life.
Yeah. So at one atmosphere, we got ice, water, and gas. And as we move along this line, what are we doing, Miss Morris? We are
going from solid to liquid, so we're melting. And then we're going from a liquid to a gas, so we're evaporating. But let's look at the melting line for a minute. I'm sorry, the boiling line.
So the boiling, that means I'm boiling is liquid to gas. So that's liquid to gas. So you're talking this line, right?
Yep, absolutely.
Okay.
And I'm actually looking specifically at the 100 degrees Celsius.
100 degrees Celsius, I'm there. Ah, got it. Okay.
So notice how it connects with one atmosphere.
One atmosphere, which is what we're at right now.
Yep, and water normally boils at 100 degrees Celsius.
So water boils at 100 degrees Celsius.
So instead of us just telling you that,
you can see it.
It's actually a true fact.
Right.
So how can we affect that boiling point?
Well, if I want to
be in Colorado.
Okay, so Colorado or Denver, yeah, like super high. I know the higher you go, the less gas molecules. It's harder, thinner to breathe.
So the pressure is actually decreasing.
So the pressure is decreasing. So the higher I go means this is going to go down. So as this goes down, I'll come over. Now, what is water? Water, liquid water. Oh, now it's a gas. And what's its temperature boiling at now?
It's less than 100.
Less than 100. You said it can get down to we're talking like 87 degrees Celsius. So check that out. Just by lowering the pressure, or the outside pressure, the vapor pressure can be lower, and we can have boiling at lower temperatures.
So it's everything that we've said earlier. So more importantly, one of the skills that we need to do is we need to be able to look at one of these graphs and answer questions like that based off of it.
Yeah. So like, for example, let's say this is 2 atmospheres. And you asked me, what is the boiling point of water at 2 atmospheres? Well, I would come over to 2 atmospheres, and I know boiling is going between liquid and gas. Okay, I got this. Now I'm at my liquid. I'm going across, and I should do this with a ruler, right? And I've got liquid over here, water, and gas over here. So going from liquid to a gas, well, right at that temperature, it looks like in order to have boiling water at 2 atmosphere, which is double the pressure that we're normally used to, you'd have to be at a temperature which is pretty high. I don't know, 100 and 374. This is probably logarithmic, but this is logarithmic, so it might be like 150 degrees C. So a higher temperature. Okay. Triple point. There it is. We've got gas. There it is. We've got gas, we've got solid, and we've got liquid, and they all exist right here. What about the critical point? What the heck is the critical point? It's a great time to write a definition.
So a critical point is actually the point at which a substance can only exist as a gas.
Substance can only be a gas.
Which makes sense because it's at a pretty high temperature.
High temperature.
And a pretty high pressure.
High pressure. High temperature means...
we're moving around really, really fast.
Which means higher energy. And we all know the highest energy state is...
the gas.
Is gas molecules, and the lowest energy is solid for most of them.
Good to go.
Okay, guys, so we're gonna use a little demonstration. We're actually going to boil water with ice, and this is going to help us understand why boiling point gets higher with increased pressure and it gets lower with lower pressure. So we've got a boiling water here, and so this is at, if I were to stick this in here, this would be at 100 degrees because it's boiling, and we can actually do that. Take my temperature. This goes all the way up, and you can see it. Right there, it hits it at 100 degrees. Oh, it's going past. And it's probably because I'm right at the hot plate. But it's about it's at 100 degrees because it's boiling. Now if I turn this off and I remove it, and then I go ahead and I cork it, I'm going to show you. I'm not going to explain it yet. Turn this upside down, and you can see this is not boiling right now. This is not boiling. Clearly is not. And you would think if I add ice to it, it's going to make it cool down. But watch this. The ice thing. Add some ice. And just watch here for a second. Whoa. And check it out. So now we are boiling the water. We're boiling the water. So water is boiling, and the reason why the water is boiling. So if you I'll kind of just point as I go. And I gotta be careful. This is still hot. So the reason why the water is boiling is because, remember, when I was boiling the flask, all that water was changing into a gas. And it was pushing all the empty air that was above the water out. And so now water vapor filled the spot where air used to be. I took it off the boiling and still water vapor, and I plugged it really quick. And when I plugged it, the thing that's filling that empty space above the water was just water vapor. I went over and I turned it over, and we all know that when we cool the water vapor, so there's water vapor in here. And when I cooled the water vapor, that water vapor turned back into a liquid, leaving a vacuum up here, or an empty space where there were no gas molecules. So the atmospheric pressure, or the pressure outside of here, has now been lowered because all the gas molecules were turned into a liquid. And the lower the pressure is up here, the less energy is required to change this liquid back into a gas. So we'll draw another picture, but basically think there's less gas molecules to keep this liquid from bubbling and boiling into a gas. And so I am just cooling the air up here. More water vapor is condensing back into a liquid, making it easier for that water to boil. And so if I were to take this temperature, it'd be less than 100 degrees. And it's boiling right now. And it's boiling. And all I'm doing is I'm cooling the water vapor. It's pretty cool. So we'll do this in class too.
Okay.
All right. So what's going on here? Ever wondered how ice skaters, they skate like they're on ice, right? It's like, Disney on ice or anything like that. It's all these shows on ice. And they're skating, and yes, ice is slick, but they're actually not skating on ice. They're skating on water. So if I was to zoom in, if I was to zoom in on her skate right here, okay? So I'll zoom in on her skate. What she's doing is on her skate, she's putting all of her weight and she's exerting a large amount of pressure. And so she's really pushing down on that ice. Okay, so this is ice right now. It's below 32 degrees Fahrenheit and below 0 degrees Celsius. So let's go back to our phase diagram of water. So here it is, and normally we're at 1 atmosphere and we're below 0 degrees Celsius. So we're about probably, the ice temperature is about right here. And that's what it is at a normal pressure. What she's doing though is she's pushing at about like 200.
Yeah, something like that.
Yeah, so some extreme pressures, maybe 15 atmospheres.
Because it's on that tiny little blade, so it's not really spread out.
So there's a lot of pressure between the skate and the ice. And so let's go ahead and take our pressure. Let's go up to like, I don't know, 50 atmospheres. So 50 times the normal pressure. Well, if I take that ice and I increase it under pressure up until it hits, up until it hits 50 atmospheres, we can see that at about right here, it's not ice anymore, it is
a very thin layer of water.
Of liquid water. So the reason why they're able to glide like that, they're actually not gliding on ice, they're gliding on liquid water. Okay, because the amount of pressure that they exerted that ice, they pushed that pressure so much that that ice turned into water. Now I didn't increase the temperature at all. I stayed on the same temperature. All I did was change the pressure. Okay?
Pretty cool stuff.
Pretty cool stuff.
Speaking of pressure.
Pencil. You got a pencil? Well,
I don't actually. Oh, I do.
Okay.
But this isn't a normal pencil.
It's pencil. But that is
our mechanical pencil.
That is graphite, right? And you told me earlier that I can make that into a diamond. Tell me now, please. I just bought one and it was expensive. How do I do that?
So one of the ways we can do it is, let's check out our phase diagram while we talk about this. Graphite is already a solid. What I want to go ahead and do is I want to make it a different form of solid. Remember, we call that allotrope. So let's check out the pressure at which graphite is normally a graphite.
Okay.
Or graphite is normally graphite.
Well, it's kind of tough to see here, but I think this says 10 to the 9, and there's some new units there, pascals. So normally, like say at this pressure, and if I'm at this degree, I'm right here. So I've got a pressure of, I don't know, 10 to the 9 pascals, and I've got a temperature of, say, 300 Kelvin. Okay, so this could be a little bit more than room.
Yep, just about a little bit more than room temperature.
Room temperature. And if I want to make that into a diamond, what do I got to do?
You are going to have to put, is it 3 times the amount of pressure?
I don't know. It's a lot more pressure clearly here. So if I increase the pressure,
another 1,000 pascals worth of pressure.
So I increase the pressure, and guess what? I drift into this purple area, which is
the diamond area.
The diamond zone. So now I can actually take my graphite pencil, and if I put it under extreme amounts of pressure, we can make a diamond. And this is where diamonds form. They're buried in the earth, and there's so much earth stacked on top of them. They create so much pressure and high temperatures.
And that's how you get those shiny rings.
And that's how you get the shiny rings, to get that bling. Okay? And that's it. So we'll pick up more with this later. Lots of practice with phase diagrams.
Yep.
I would encourage you to kind of quiz yourself, saying, okay, what if I'm starting here and I want to make it a vapor? Well, I can do it by heating the temperature. Okay, and I'd have to heat it up until this point. Or what happened if I was at 2,000 Kelvin and went to 4,000 Kelvin?
Yep.
So we'll do a lot of quizzes and stuff like that in class.
Make sure you write down all of your phase changes.